Hello, everyone. Let me try that again. Hello, everyone, and welcome to 8.2. We're going to be pretty short video today. 8.2 is a huge section in the book, but we're going to be taking out a lot of the extra stuff. So, what I expect you to do after this section is going to be different from what the book expects you to do for this section. And check the homework assignment for details. And I try to give very specific information about what I want. So essentially right here in 8.1 was everything about the graphs of sines and cosines, all right? We talked about amplitude, we talked about phase shift, period, we talked about the midline, all that stuff for sines and cosines. Now this section is supposed to be that much in depth for the other four trig functions, tangent, cotangent, cosecant, and secant. But we're going to be a little lighter on these topics. The biggest thing I want you to do from this section is know what these graphs look like, okay? And then a couple things are going to carry over from the previous section as well. Probably the hardest thing that's going to be in this section is going to be asymptotes. Okay, so let's look at some of the graphs. And again, it's very, very important that you are familiar with the graphs of these four trig functions. So as you're going through this video, include these in your notes where possible. So the first graph that we're going to look at is going to be tangent. Okay, so tangent looks like this. It has an infinite number of asymptotes, and specifically, what we have for tangent is this. Okay, so tangent of 0 is 0. You could plot some other points. Another really nice point that we know is tangent of pi over 4 is 1, right here. And then if we zoomed out a bit, you can see what's really, oh my word, that, oh, that's not good. Hold on, different strategy. We zoom out a little bit, or if we just look at this, you see that the graph will get closer and closer and closer to pi over 2, but it will never reach it, and it shoots off to infinity. It's going to be an asymptote. Okay, all of these graphs are going to have asymptotes. If you ever forget what the graph of tangent looks like, just plug in some points on your calculator. 0, 0 is a good one. Pi over 4, 1 is a good one. You could do other special triangles as well. Like pi over 6 and pi over 3, and then I'll give you some approximations. Pi over 3 is around here. But again, the important thing to know for the graph of tangent is that it kind of looks sort of like a cubic function, but it does have those asymptotes. Again, there's an asymptote at pi over 2. There's an asymptote at negative pi over 2. There's an asymptote at negative 3 pi over 2, and positive 3 pi over 2 are infinitely many asymptotes. We'll talk about where the asymptotes are later. All right, so as a pair of this, right, since we're talking about tangent, let's also talk about cotangent, okay? So you notice, right, cotangent and tangent almost look exactly the same, okay? One is just going the other direction and is a little what do you call it? Is a little reflected and shifted, right? And again, the relationship, these are inverse functions of each other, right? Cotangent is just 1 over tangent. So the inverse of 0, the reciprocal functions, not inverse functions. That's the next section. Reciprocal functions. So what is the reciprocal of 0? Well, the reciprocal of 0 is undefined. And as you can see, cotangent, the blue thing, is shooting off towards infinity at 0. Right here you can see, well, what is the reciprocal of 1? If you flip a 1 upside down, it's still a 1. So that's why this is on both graphs. And likewise, the red one, tangent, has an asymptote at pi over 2, and the reciprocal function cotangent has a 0 at pi over 2. So tangent and cotangent are very closely related, as you can see here. And so if you recognize the shape, then you can say, okay, this is either tangent or cotangent. And then all you have to do after that is just plug in a couple points to see which one it is. All right, so that's the method to recognize tangent and cotangent. So let's do a couple problems with tangents and cotangents. All right, so example 1. Actually, before we get into example 1, sorry about that, let me talk about tangents and cotangents, okay? So, for a function y equals a times the tangent of bx, there's a, oh my word, there's a couple things we can say about this graph, okay? Specifically, a is what we call the stretching factor, right? Very similar to when you're dealing with sines and cosines, where a was the amplitude. Here, amplitude doesn't really make any sense, but it's still a vertical stretching, all right? And let's go back to the graph real quick. Let's go back to the graph right here and ask, what is the period of tangent? The period of sine and cosine was 2 pi. Well, the period can actually be seen pretty easily if I just plot these extra lines. All right. You can see between this green and this blue line that it has essentially the entirety of one piece. All right. The entirety of this one piece, and then it repeats forever. So that is exactly what we called a period. So what's the distance between these two lines? Pi over 2 and negative pi over 2, the distance pi. All right. So just very, very similar to sines and cosines, the period here is going to be the normal period, and with sines and cosines it was 2 pi divided by b. But because the period of a normal tangent function is just pi, here our formula for period is going to be pi over b. So those are two things that we're going to talk about for tangents. And the last one is probably going to be the most difficult, and that's the equation of the asymptotes. Because remember, there are infinitely many asymptotes, right? This green one is an asymptote. This purple one is an asymptote. There's another one right here. And if we zoom out, right, we did this before, you can see that there are infinitely many asymptotes. All right. So how can we find them all? Well, we just look at them. Pi over 2 is 1. But remember the whole idea of a period. The whole idea of a period is that it repeats after that amount of time, or that amount of x value change. So we said our period here was pi. So theoretically, there should be an asymptote every pi. So if we add pi, we get to pi over 2. Hey, there's an asymptote here. If we add pi to pi over 2, we get 3 pi over 2. Hey, another asymptote. Add another pi, asymptote. Add another pi, asymptote. Add another pi, asymptote, etc. So we can come up with an equation for every single asymptote by just looking at the first one. So let's leave a blank for the first one, and then adding a bunch of pi's, or a bunch of the period. But here the period's not pi, right? The period for a general tangent is pi over b. And then we just add a bunch of these. So right here for k is any integer. So we can add multiples of pi. All right. And the question is, what goes here? What's the equation of the first one? So let's go back to tangent. What was the first one? The first one's pi over 2. But if b changes, it's not going to be pi over 2 anymore. But what it is going to be is it's always going to be half of the period. So half of the period is going to be pi divided by 2b. Okay, so remember, it repeats every period. And the first one is always at half the period, unless there's a phase shift. But I'm pretty sure we don't, pretty sure we're not going to talk about, nope, we are going to talk about phase shifts. So there might be phase shifts. All right. If there's a phase shift for this one, then you just shift this first one over by the phase shift. All right. So with that in mind, let's do some examples. Example 1. Find the stretching factor the period, and that has a O in it, and the asymptotes for the below ones. Okay. Also, notice I didn't give you any information about cotangent, and that's because it's very closely related to tangent. All right. Should be able to figure that out. So let's start with the easy one. F of x is just equal to tangent. Let's start with the default, the basic tangent function, using this information that we talked about in general. Okay, so here, the stretching factor, well, a is 1 here. Stretching factor is 1. The period is unchanged, so it's just pi. On the asymptotes, this is where it gets a little tricky. The asymptotes are going to be x equals half of the period, which is pi over 2, plus the period, which is pi times k. And again, that's the whole point of a period, is because it always repeats every period. Every periodic function repeats every period. So this will repeat every pi, sine and cosine repeat every 2 pi. All right? And that's it for A. And this is really a big chunk of your homework assignment, is doing this sort of thing, albeit with more complicated functions. All right. Let's do another one that's more complicated. F of x equals 2 times the tangent of 4x minus 32. All right, so this one is, of course, more complicated. And the phase shift is going to be useful here. So it would be in our best interest to find the phase shift. All right. So what we have here is the stretching factor is, again, just going to be that number in front of the tangent. It's going to be 2. Just like the amplitude, A is A, for sine and cosine, which is the number in front of the sine or cosine. So the stretching factor is 2. It's a vertical stretch of 2. We know the period is going to be pi divided by b. B is 4. So the period is just pi over 4. Okay. And we're not asked to find the phase shift, but let's find it anyway. And the phase shift is going to be exactly the same as it was for sines and cosines. It's going to be 32 divided by 4, c over b. Oops, I wrote b instead of 4, which is just 8. So we're shifting everything 8 units to the right. Shifting things 8 units to the right is a little tedious when our period is with pi's, but it's okay. So the asymptotes is going to be always the line x equals, and normally it starts at half the period. The first one is normally at half the period, which in this case would be pi over 8, but remember our phase shift. This shifts at right 8 units. So we're going to add an 8. So that's the location of one of our asymptotes. And then we just add the period times k, so pi over 4k, and that includes all the other ones. All right. And that's all we're asked to do. On the homework assignment, I asked you to graph it, but I specify under the assignments tab that you don't need to graph it. It's a good idea to graph it on a graphing calculator or a computer to kind of visualize what's going on, but you don't actually have to graph these by hand. No, graphing these by hand is way more than I would expect from you. So let's go see if our answer is correct. So the graph is y equals 2 tangent of 4x minus 32. All right, so we're going to have to change our scale. Let's see, the period is pi over 4, so let's look at a negative pi to pi. So we'll see a couple periods. And the step can be, let's say, pi over 8 or something like that. The y-axis is pretty good right here. So we said the stretching factor was 2. Okay, so what that means is when we go pi over 4 over, or not pi over 4, when we go a quarter of the period over from our starting point, we'll be at 2 instead of 1, which is exactly what we have right here. We said the period was pi over 4. Well, it's a little hard to see here because we have a weird phase shift, but pi, remember, is about 3.14. Divide that by 4, and you're going to get about 0.75. And yeah, these x values are about 0.75 apart, and that's where it repeats. Okay? So that's pretty good. We said the asymptotes, were a pretty ugly one. All right? So we're going to just use a calculator right here. All right? We said one of our asymptotes was at pi divided by 8 plus pi over 4 times k. Let's have k be 0 to start off. So this tells us that one of our asymptotes should be at around 8.39. All right, so let's change our units to be something we can see a little bit more easily. Do we have an asymptote at 8.39? 8.39 is like right here. Yeah, looks like there's an asymptote right there. Good. Let's check where another asymptote was. Let's multiply this by another integer, say -2. This says there should be an asymptote at 6.82. 6.82 is around here. And yeah, there looks like there's an asymptote there. So it's a pretty good indicator that we did our work correctly. Checking your answers with graphs. But no, you do not have to graph this by hand, even though the book tells you to. All right. So let's do a cotangent one. Part C. So we didn't explicitly talk about cotangent, but it's going to be very similar. All right, let's go g of x equals, let's just do the basic cotangent function, okay? Just cotangent of x. So we need a stretching factor. In this case, it's just the number in front of the function, which is 1. The period. Cotangent and tangent are essentially the same things, okay? Well, they're just reciprocal, so they're going to have the same period, pi divided by b. In this case, it's just pi. The asymptotes are a little bit different, but it's the same idea. Find the first asymptote, and then just add periods. And remember back to the graph of cotangent, okay? The graph of cotangent, if we go back to a normal x step size of something like pi over 4, this is really nice because cotangent always has an asymptote at 0 unless we have a phase shift. Okay? So your first asymptote here is always super easy. The first asymptote is just 0. So we just add as many periods as we want, and our period is pi. So here's just pi times k. And you can see that over here, right? Pi times 0 is 0. Yep, there's an asymptote. Pi times 1 is pi. Yep, there's an asymptote. Pi times 2 is 2. Yep, there's an asymptote. Times 3, yep, asymptote. Yep, asymptote. Yep, asymptote. Okay, so we know we're good on this one. So let's finish up part D. Let's look at a transformed cotangent function. H of x is equal to 3 cotangent of pi x. This is a cute little graph, okay? This is a cute one. All right, no phase shift, unfortunately, I'm sorry. But our stretching factor, A, you can write A or stretching factor, I'm gonna abbreviate here, is just 3. That means it's going steeper than usual. All right, and our period is going to be pi divided by b. Well, b is the number multiplied by the x. B is just pi. So our period is pi divided by pi, which is 1. Aha, what a nice number. And our asymptote for cotangent is always the first one. Remember that cotangent's first one is at 0. So it's always going to be 0 plus the period. I don't need to write a plus here. And the period is 1 times k. So the asymptote is just x equals k, where k is any integer. Let's look at this graph. Cute graph. Okay? Y is going to equal 3 times the cotangent of pi times x. That's a cosine. That's a cosine. All right, and let's look from -5 to 5 with step size 1, and then maybe say -3 to 3 or something. Oh, this is too big of an x thing. So this is cosine. It's getting stretched pretty big. Let's make this like -10 to 10. Make it a little bit more cotangent-y. All right. So look, stretching factor is 3. So when we go a quarter through the period, we are at 3 instead of when we normally be at 1 because we got stretched. We said the period was just 1. So look, -0.5, 0.5, 1.5, 2.5, it repeats every 1 unit. Great. And then we said the asymptotes were at k, where k is any integer. So integers are like 0, 1, 2, -1, -2, -3. These are all integers, and they all have asymptotes right there. All right. So we got it. Easy as 1, 2, pi. Okay. So we're going to finish off this video today with introducing the other two functions that we're going to talk about, and then we're going to save those problems for tomorrow. Tomorrow will be a little bit longer of an exploration. So these are the really good ones, right? Because if you remember cosecant is just the reciprocal of sine. So let's look at the graph of sine and the graph of cosecant at the same time and see what we're going to get. And we're going to get something pretty interesting. Okay, so let's make sure we got our scale good. And actually, this is a pretty good scale we have right here. So this is sine. We all know what sine looks like by now, right? Period is going to be 2 pi. And it oscillates between 1 and -1, where every quarter of a period, it either goes to the midline or a max or min. So midline, max, midline, min, midline, max, midline, min, etc. Okay? Let's look at its reciprocal function, cosecant. So that is something, isn't it? So let's unpack this a little bit, right? So on sine, when sine is 0, cosecant is a reciprocal function. What's the reciprocal of 0? 1 divided by 0. That's undefined. So every time sine hits 0, cosecant is going to be undefined, and we're going to get another asymptote. What else do we know about cosecant? Sorry, what else do we know about sine? When sine of pi over 2, sine of pi over 2 is 1. The reciprocal of 1 is just 1. So every time we're at a maximum or minimum, sine and cosecant are going to overlap. Okay, so we know asymptotes, we know overlapping, and we can plug in a couple other points, and you're going to get what kind of look like parabolas. They're not actually parabolas, but they kind of look like them. They're like parabolas with asymptotes. Okay, so cosecant looks like that, which is kind of crazy. All right, and similarly, right, we have a very similar story with cosine and secant. The reciprocal of cosine of x is secant of x. And you might say, isn't this the same picture? It's almost the same picture, right? Sine and cosine are essentially the same graph, just shifted over. So it makes sense that secant and cosecant would essentially be the same graph, just shifted over as well. So this is the exact same shape, but the asymptotes are in different places, okay? We can look at them together, right? Secant and cosecant, the red and the black, they're almost exactly the same, right? Red is just shifted over a little bit. All right, so we're going to talk more tomorrow about how to find the asymptotes for this. Spoiler alert, the period here is going to be 2 pi. All right, why is it not showing the x coordinates here? Ah, there we go. Period's going to be 2 pi. And you might think, but there's an asymptote every pi. Why isn't the period pi? Well, because it takes 2 asymptotes for this thing to start repeating. We've got kind of an upward doot-dah and a downward doot-dah. And we need to have both of them before it starts repeating. So that I keep double clicking as if double clicking is going to show you something. All it does is zoom in. So 0 to 2 pi, and then we have another positive and negative doot-dah. Just like sine and cosine have periods of 2 pi. So we're going to talk about asymptotes of this. We're going to talk about stretching factors again. We're going to do a couple more like we did today. And then really we're just going to kind of go the opposite way and try to find equations based off of graphs. Nothing too bad. Okay, I'm hoping 8.2 is going to be a lot more pleasant than 8.1 is for many of you, but we'll see how it goes. Anyway, as always, if you have any questions, send me an email and have a good day.